Aipd, Army Corps, Army Professional, Army Institute of Professional Development, Army Correspondence Course Program. Chapter 1. Chapter 1 discusses the fundamental of railroad engineering. If you study how the railroad meets operational difficulties presented by terrain over which they travel, has become as familiar. Such terms as grade, alignment, profile, gauge, cross, level, surface, and track and clearance, and the relationship to railroad engineering and to the job of the track supervisor. 1.3. The effective grade of the railroad location. The bulk railroad locating has been done. In some cases, location 1.3. Effective on the grade of the railroad location. The bulk railroad locating has been done. In some cases, location was wisely chosen. Other choices was poorly made. The location engineers had to solve numerous economical technical problems. However, you may look at it good or bad, or the 5 railroads have been built aside of the extension relocations. The kind that work is no longer the major concerns. However, the endeavors then should be directed not toward learning how to locate a railroad, but rather toward understanding construction elements and why the railroad was built as they were. Only then will we have a proper appreciation of the sound program of maintenance. 1. The rack railways. To eliminate slippage of locomotives driving wheels of steep grades, a rack railway was placed between rails. The rack is turning the mesh with a gear wheel of the or pinion of locomotive. The locomotive so equipped was also referred to as a cogwheel locomotive. 2. Inclined planes. To overcome a steep slopes, engineers built an incline requiring standard engines at the top of each grade. Training traveled over the level tracks as far as possibly when they are pulled extremely steep grades by cables attached to the stationary engines. Afterward, trains proceeded to the next incline where they were left down and pulled up the succeeding hill. This operation may be compared to that as a canal or locks, the plane corresponding roughly to the locks. Tangent and non-tangent lines at end of the arc is shown in Figure 1.2, stagnants and the curves in Figure 1.3, the curvature easement right of way of 3 items which you should be familiar with alignment and studying. The tangent and the curve easement, the right, and 3 terms in which you are familiar should be familiar with alignment. Gravity line of the inclined plane from city to city and development line and the course of elevations. 1.4. Alignment. The path the railway follows is known as horizontal alignment, simple alignment, and it may be defined as a ground plan railroad is distinguished from its profile, or in a profile you see ups and downs in the railroad path, but on the ground you see stretches of straight track connected by arc curves. The 7 straight stretches are referred to as tangent arcs. Curves by definition, the tangent is a straight line that touches the circumference of a circle at any only point, a point of tangency. Origincy of the circle drawn to the point of the tangency perpendicular to the tangent of the radius. The tangent from the right is or 90-degree angle. The arc is any part of the circumference of a circle is formed by drawing a non-tangent line other than the diameter than through the 2 points on the circumference. Tangent, non-tangent lines are shown in Figure 1.2. Tangents, curves in Figure 1.3. Curvatures, easements, right away in the 3 terms on which you A. Curvature. The measure amount of the curving is known as the curvature. It tells whether or not the curve is sharp. The sharpness of the curve depends upon the length of the radius of the circle, which is in the arc of the radius long, and the curve has light curvature. It is not sharp. Conversely, with the radius of the short, the curve is sharp. In some countries, the sharpness of a curve is measured in the terms of radius. In the United States, the curvature is measured in degrees. The geometry of this measurement discussed in Railway Tractor Maintenance 2 is sufficient for now that you know that the larger the number of the degrees of curvature, the tangent line and the right angle and the radius and the other right angles of the arc on a non-tangent line. The curves follow the tangents and right angles. The easement is actually placed at the end of the curves, flattened by out the provided the smooth ride for trains. The flattened out portions are called the easements and transition curves. Geometrically, they are segments of spirals. However, they are not discussed there, but they're in the Railway Tractor 2 maintenance. Track maintenance 2, they were treated in some detail. See the right-of-way as mentioned earlier. The path of railway follows known as the ailment and is made by curves and tangents along with a line of various structures of facilities, towers, stations, fences, bridges, tunnels. The strip of land occupied by the tracks and other structures is called the right-of-way. A legal definition of the right-of-way: the authority of the railroad holds the land over the travel but is interested in meaning the first referred to is strip of land unless otherwise indicated by the term right of way as used in track maintenance by means of property itself rather than the right which the property is held. Used to show the center line, a typical example is used on the railroad diagram is seen in Figure 1615 is a profile when looking at a surface of the railroad from the side of vertical projection. The ups and downs are visible, horizontal curvatures are no, and are not. Picture of the railroad from the side is known as a profile. Ups and downs are referred to as grades, and in the country of the steepness in the grade is given to the percent arrived by dividing the vertical rise by the horizontal length at a grade of multiplying the result by 100. A simple way of determining percent grade is to find the rise of the feet over the horizontal distance of 100 feet. This gives the percentage grade. For instance, if a rail rises 1.5 feet, the horizontal distance is 100 feet. As shown in Figure 1.4, the grade is 1.5%. Irregularities of the terrain make the changes of rate of the grade of the rail line necessary. However, the abrupt changes are not permissible. You can readily imagine a result of a speeding train coming down a 2% grade, suddenly hitting level tracks, and the impact of the front wheels hitting the level tracks would damage the locomotive and the tracks. Further, if we change the grader with it where greater enough, the center section of the locomotive would be lifted off the track and derailed. 1.5% over 1.5 feet of 100 feet. The percent grade is 1.5. 15 over 100 times 100 is 1.5. By using vertical curve where the different gradients meet to solve the problem, the angles formed when the grade must meet 10 must 10 be eliminated. They must be connected by the curve. Length of the curve depends upon the size of the angle, the length of trains traveling over the line. The Figure 1.5 illustrates why the long trains and sharp angles and require long vertical trains. No vertical curve on the impact the vertical curve, and no vertical curve up and over in the vertical curve of up in steepness and downness. In the United States, the standard gauge is 56.5-inch gauge. Sides of the rail gauge measured of the gauge side of the rail. The opposite side of the called is called the field side. Before rail is placed in the track, it has no gauge on it or field side. Once it is laid by the side facing the center line of the track becomes the gauge side, and the side facing away the center line becomes the field side, as illustrated in Figure 1.6. Developing of the standard gauge. Some rail lines with or borders have different gauges. For instance, 36 inches of the Rio Grande line of the Rocky Mountains. Such lines are known, but ended up in the 19th century that they were common until 1886. The railroad in the South were predominantly 60 inches in gauge, but some important lines as Erie of the Missouri Pacific were originally laid with the gauges of 72 to 66 inches respectively. Necessary gauge variations. You know that the standard gauge of the United States to certain other countries is 56.5-inch gauge. Now you are going to learn the gauge that doesn't always measure a 56.5-inch gauge between the rails to prevent the binding in its being found necessary to broaden the gauge and sharpen the curves, as shown in Figure 1.7. In some cases, the gauges become 57-inch or greater. Of course, the odd gauges are those other than 56.5-inch gauge are also increased in the sharp curves for the same reason, and the gauge is also widened on the inside of the low of the rail. Cross level, the height of the elevation of the two rails make the track in relation to the other. The cross level of the track, among the other effects of the trains that move over the rails. Good maintenance requires proper cross level as illustrated. Proper cross level for the tangent track, proper cross level for the curved trap super elevation. A track clearance of the diagram is prepared in each sentence of the section of the railroad showing the maximum dimension of the railway equipment loaded in the passage over the line. The clearance chart is the primary importance. Those transportation department whose most route out odd-sized shipments is almost important that the maintenance official He must be careful not to restrict the existing clearance in the maintenance work. For example, cannot raise the track, tunnels, or under bridges without authority of the higher headquarters, nor may he change alignment if such restricting elements or structure or walls are nearby. The proper face and the poor surface. A track clearance chart or the diagram prepared for each section of the railroad showing the maximum dimension of the rail equipment or load that can be passed over the line of the clearance. The chart may be of primary importance to those of the transportation department whose must route odd-sized shipments. Also important, the maintenance official, since he must carry not to the restrict existence clearance of the maintenance work. For example, he cannot raise the track in tunnels or under bridges with authority from higher headquarters, nor may he change alignment if restricting elements as structures of the walls are nearby. 56.5-inch gauge B, wide in the sharp curve, sometimes but narrow. Higher speed cross level refers to the relatively high of the two rails. Surface refers to the smoothness of railway equipment. Must conform to certain clearance limitations. Each section of the railway has its track clearance chart or the diagram showing the maximum dimensions of the rail equipment loading that can overpass the line. Maintenance personnel must observe clearance limitations, also especially raising the track level in tunnels for changing alignment in structure walls. See your clearance diagram of the railway bridges and clearance diagram of a single track tunnel track to the tangent. A road bed is strip of terrain that varies in width of 18 feet of the single track tangent of 3 feet of the double track of curb. The road bed follows the line of the road if provided means of holding in tracks and surrounding the land so that the water cannot remain on them. The ballast laid upon the subgrade distributes the weight over the terrain in wide areas so that the ground can support as a figure. The road bed is concentrated over the load of the train. The load is spread over the cross ties over the subgrade of the earth. The load spreads over the ballast, and the load spread over by the rail. A road bed is a strip of terrain that verifies that from 18 feet of the single track tangent, 33 feet for the double track of the curve. The road bed follows the line of the railroad if provided by the means of holding the track above the surrounding land so that the water cannot remain on them. Base laid upon the subgrade distributes the weight of the train over the wide area so that the ground can support, as shown on figure 2.1 shows. If railway equipment is directly supported by the rail's track, each rail is supported at the intervals along with the length of the cross side of the rail, therefore acts as the girder between the ties, and the ties support the rail and turn are supported by the ballast laid on the subgrade. 2.3 Terrain irregularities. The roadbed compensates for the minor terrain irregularities, filing the low spots fills and cutting the high spots of the cuts. The two type of cuts, side hills through the diagram of the figure 2.2, but where there are the fills cuts and they are shown there are slopes where they are. Slopes are the problems, erosion, stability in the following subparagraph slide and through the cut fills, slopes, and are discussed. A side hill cut with a fill and earth removed over the cut. Through the cut, earth may be removed 1.5 by 1. A combination of the rock soil through the cutout. The rock and the material removed. Note that change the slope from the rock to the soil. In a side hill cut, the roadbed surface lies partly above normal level of the ground. The earth which must be removed in making the cut may generally be dropped over the other side of the proposed track line to provide the material. In through the cut of the entire roadbed lies between the normal surface of the ground. If fill in the entire roadbed lies in the normal surface of the ground, fills are used and avoid the building bridges over the ravines over the low areas. Slopes are inevitable whether they cut the fills or whether they are slopes, so you can expect the erosion stability problems, although the design of cuts and fills and slopes construction problems that does not come up to the scope of its text, and the track supervisors as well as informed on the design can prevent supervisors who are well informed on the design can prevent the necessary majority of the repair work and can make minor repairs on the poor decision creates. Designs of the slope used in the cuts and fills depends on the knowledge of soil stability and the rock formation. A few simple rules to guide the track supervisors are given below. Ordinary stability Ordinary stable soil may be stopped at the ratio of 1.5 to horizontal, 1 vertical. Without the danger of sliding, the rock may slope at the ratio of 1/8 to 1/2 the horizontal, 1 vertical, depending on the formation and composition of the rock. Cuts and sometimes made from the combination of the rock soil when encouraged to stop at the change to the point of the rock changes in the soil of the cut. Shown in Part C, the figure 2.2, the rock is in the lower section of the cut. The two erosion is the one thing that the track supervisor must constantly guard against unprotected slopes, and the cut may wash away. Then heavy rainfall covered the track with dirt. Operations must be halted until removed until on a fill. The washout may leave with the track unsupported and again bringing out operations to standstill until repairs are made. Commercial rails lines really rely on dependently of the business. Military lines being main supply routes must be kept open. Therefore, the occurrence of washouts must be avoided. 1. Intercepting ditches and dikes are discussed in Section 2, which the track drainage is discussed in detail. The planned routes hold the soil together, giving the additional stability for civilian railroads, introducing planting growth serves for the further purpose of beautifying the right-of-way. Consideration often underrated in the importance competitive transportation market. A wide variety of vegetation can be used as honeysuckle shrubs, vines, roses, various pasture sods. Experience shown in the vegetation slopes pays itself as many times as eliminating over other costs of maintenance. Whether the space is not permanent, proper sloping while the slope persists in sliding, usually remedy to construct the remain of the wall of the foot of the slope that may be concrete and stones, timbers, discarded cross ties. 2.4. The ballast. The ballast is laid upon the subgrade of the prepared dirt surface of the roadbed. The good ballast material should be workable, during and strong enough and resist crushing in angular shape to resist movement to the permanent drain, which, when compacted, the ballast supported the cross ties resisting up upon holding them firmly in the place with there maintains the alignment, provides the uniform support of the track and proper structure distributes traffic weight evenly on the roadbed. The ballast provides a flexible base so that the ties can be removed to adjust to the rails of the proper alignment of the surface and reduces the dust and deaders to the growth of the vegetation along the tracks. The following 3 paragraphs discuss ballast materials, the selection, and the ballast selection. 2.5. The ballast materials. Materials for the ballast are the application greatly of the ballast materials chosen depending on the location and on the kind of the traffic, especially expected high-speed, large volume, heavy tonnage traffic all justify expensive ballast. The type of roadbed also influences the ballast. A high-level fill of the drain stable soil does not require the most ballast as a cut, whether or satisfactory drain is hard to get. The materials used in the ballast depend on the availability of the cost. Brief discussion of the properties and the more common ballast materials follow. Gravel inadequate quantities usually available for the most roadbeds and for the local gravel pits. The gravel is now known as a pit run, unprocessed to make. Sometimes be used in ballast as it comes to the pit, but usually screened and washed before. In good gravel, the ballast contains only a small quantity of dust and sand for the tracks used for light service, such as branch lines, passing yard tracks, and it is unnecessary to wash, screen, and for the gravel. However, the heavy service expected pit run gravel is to be used. It should contain no more than 2% dust and 40% sand. No more than 40% sand. The percentage is determined by weight. Slag is a waste product of the furnace of the reduction of the ore. For the railroads running through the near locations of the large quantities iron and other metals are processed slag and abundant, cheap, and however it should be used in the caution because quality varies widely. Good slag ballast is free from the dust and has excellent drainage qualities. The better the slag, the ballast compares favorably with the crushed stone. See, the cinders are residues. Cinders are residues from coal used in the furnace advantage. The cinders are ballast. Ties are then fine drainage properties easier than handling, although cinder ballast is quickly reduced to objected dust under the traffic. It may be used in yards, and sift cinders are easily obtainable and economical. Sand, work plentiful, is sometimes used in the ballast as advantage to excellent drainage economically. However, it does not make a good ballast for several reasons. It easily wash away, blown away, or creates a considerable dust problem in the dry areas. Marking makes the track surface difficult, and sand should be used in the ballast only as an expedition on light traffic roads. F. For other materials used by the ballast include the shells, small pieces of the ore stone mixtures called chats, and impure dull-colored flint-like quartz called cherts. However, they are seldom excel from the quality of cinders or gravel. Selection shall be made. A selection of such material must be made on the same bias as other orthodox ballast materials. They must be free of dust and must also be be able to withstand the wear. To ensure the ballast will hold the track in place, the cross ties are submerged into until on top the only to the top 2 inches are exposed, as shown in Figure 2.3 of the anchors of the tie placed almost permanently, since the track must adequately drain the pipe. Ballast must be deep enough and drain all off of the water falling on the running over the track. Military specifications require a minimum depth of 4 inches under the tie bottom and 8 to 10 inches preferably. So paragraphs A and B, the details are given in the ballast section. The military main lines, other and less than travel ones, 9 inches from the center of the rail off to the sub ballast grade, 4.9 to the end of the edge of the gravel before the tie from the center of the tie, split in half. The 2 inches above from the 2 inches that are not exposed in subgrade, 6 inches. A minimum for desirable 8 to 10 inches as in the ballast, and B a 0 to 8 inch desire in the subgrade. 1 by 1 or 2.1 slopes in toes. To ensure the ballast will hold in the track place, the cross tie submerged in it and until only the top 2 inches are exposed, as shown in Figure 2.3. This encourages the tie in place almost permanently, since the track must adequately be drained and the ballast must be deep enough to drain for all the water falling on the running over the track. Military specifications require a minimum depth of 4 inches under the tie bottom by between 8 to 10 inches are preferable. Subparagraphs A and B details are given in the ballast sections for the military and lines and other less heavy traveled ones. 2.8 Submarine. The roadbed provides a mean of holding the tracks above the surrounding land and preventing water from standing on the tracks. Minor terrain irregularities of the right-of-way compensated by filling the low spots, cutting through the high spot slopes of the roadbed must be protected by the erosion ditches and dikes. Some materials such as rock, cinders, slag, gravel, sand is used in the ballast to stabilize the tie. Distribute the weight of the train to the roadbed of the aid of the track drainage, and the amount of depth of disposition of the ballast in Section A are governed by the traffic and the terrain. Section 2, Drainage. 2, General. The adequate well-drained track is essential for the operating of the railroad. Water and damage causes constantly threaten the track because, in particular, all major track damage can be attributed directly and indirectly to the water. The time and effort spent for the achieving and maintaining adequate drainage are never wasted. However, the ideal roadbed drainage is difficult to achieve because of the few track. Pumping ties is heavily loaded in the train passing over an inadequate drainage track. Force ties down into the ballast, pushing the ballast into the subsoil of the railroad boat after each train passes the resiliency of the steel rails. Lifts the ties, leaving a hole under each tie. After numerous trains of the passes the movement of the ties, the pumps water into the already formed holes of the water rots in the ties. Water pockets continually adding the ballast under the pumping ties eventually results in a large accumulation of porous ballast deep into the roadbed, sometimes a depth of several feet. Surrounding the subsoil, the impenetrable the water collects in the porous material that cannot drain out of the water pocket forms. Obviously, a water pocket does not offer the same resistance train loads as a solid roadbed, such as variable support of the result an uneven track and spongy roadbed. Adding ballast penetrable by material at soft spots in the attempt to achieve uniform support, and only increase the size of the water pockets forced by the subsoil up into the ballast section, cutting off possible drainage for the ballast. Water pockets can present the problems in deep cuts and fills and under heavy traffic and freezing weather. 1. Deep cuts. Water pockets commonly occur in deep cuts where adequate drainage is extremely difficult to establish. Such cuts are known as wet cuts. Water pockets can result in reduced train speeds, excessive track maintenance. 2. The fills of water pockets fills in spite of the easement of drainage normally expected to prevent the pockets and fills of embankment. Water pockets are dangerous and are economically liabilities, and embankment water pockets that may cause to fill the fail just as the train passes over the track here, and they can be caused by using the small amount of the porous materials proportion to a large amount of impenetrable soil in the original construction of the embankment. 3. The under heavy traffic operating numerous heavily located trains over the lines of the poor ballast is often reasoned by the 28 water pockets forming. Water pockets forming the ballast is compressed under the ties when the rail line and either new, recent, and repaired water pockets soon from the same recent particular traffic over the line is heavy. 4. The freezing weather in the water pockets allowed to remain until winter and the freezing temperatures cause the ice to form in the pockets as the ice expands. The heaving the roadbed soon appears uneven. The track and lead can be leveled only by adding shims bearing pieces of used rails to the low spots. Since shims are placed either between a tie or a tie plate between the tie and the rail, draining the water pockets has to wait until the spring is thawed. The amount of labor and material made or needed for the stage is much greater than required earlier to eliminate water pockets. 211 Correction of water pockets. Water pockets are simply another drainage problem, and they can be continually aggregation for the subsoil stability of the track location must make or makes drainage a serious problem. For example, wet cut is typically such a location. A classic solution of the wet water pocket problem is construct a cross drain from the location of the pocket of the side ditch to the areas of the water away from the roadbed. Now that the water has weighed out, the problem is solved. The cross drains are discussed in paragraph 215, shown in figures 2.8 and 2.9. Side ditches are discussed in paragraph 214, and examples or one is shown in 2.5. And grounding, another method used in correcting the water pocket, is discussed in paragraph 215d and illustrated in figure 210. Here you see the path of water in the top ballast, subballast, and subgrade in the main longitude drainal ditch. Gravity provides a universal force to satisfy the first need. It is only necessary to provide a path. It is required for the gravity will move the water through it. Only one function of the ballast is provided by the drainage. Good ballast is porous to the rainwater for other sources falling in the track passes through the easily finding in the way the impenetrable subgrade for the water passes through the subballast over the subgrade and into the drainage ditch drain as figures of 2.5 shown as road earlier. See figure the water 2.4 the water pockets may result in forcing the subsoil into the ballast. There may be a hamper of drainage then to the ballast into the dust or fine dirt. Cinders blown on to the track may be obstructed drainage. Severely contaminated ballast but must be cleaned or replaced. Cleaned or replaced. 2.3 The correcting contaminated ballast. Whenever the ballast becomes contaminated, the drainage seriously impaired, it must be cleaned and cleaning impossible. Replaced. Usually the first sign of the poor track surface, the one refuses to remain corrected for any length of the investigating such spots generally reveals poor damage in pumping ties. Not all types of ballast can be cleaned. Pit run gravel cinders are usually replaced when they are become too dirty or severe or to serve as satisfactory ballast. However, crushed stone and tap rock is also easily cleaned. Screen gravel ballast can also be satisfactorily cleaned. To clean ballast is dug away, then the tie screen and fork. The following methods are used. 1. Stone slag screen gravel ballast. To clean the stone or slag screen gravel ballast follows the steps given. Remove the shoulder ballast for the ballast for the ends of the ties outward of the track down to the subgrade. Remove the ballast from the cribs and space between the ties down to the bottom of the ties. Remove the ballast from the space between the tracks down to 6 inches below the bottom of the ties down to the subgrade. If the ballast below the ties is less than 6 inches deep, clean up the ballast. Remove using ballast forks or screens. Replace the cleaning ballast and add new ballast when needed to achieve the required ballast section. B. The pit run gravel cinder and blast. In cleaning pit run gravel and cinder blast follows these steps. Remove all ballast except for the directly under the ties. Rest of the subgrade. Add new ballast. Raise as required. Railway track 2 maintenance 2 explains the procedure in more detail. Mechanical cleaning in recent years for many civilian roads have been found costs of cleaning log stretches of the ballast. Manual methods of given in subparagraph A and B to be prohibitive because of the tremendous labor requirements. Civilian lines were resorted to mechanicalized methods of cleaning ballast. One type of machine that they use moves along the track, digging up the shoulder between the track of the ballast, screening and replacing it. However, the ballast cleaner does not remove in the screen crib the ballast. Only one widely through their crib ballast, eventually replaced the shoulder between the track ballast and tamping seams supported by success mechanized ballast cleaners. The initial cost of the machines is high and they must be kept and constantly used to justify the investment. The frequency of cleaning, actually inspecting how badly the ballast is contaminated, are the only one way to determine the frequency of cleaning. However, the experience shows that the track terminal usually requires the ballast to be cleaned every 1 to 3 years. Heavy traffic of the roads for every 3 to 5 years, and light traffic every 5 to 8 years. Here you see the flow of water of the ditch and the railroad going the same way. through the level cross levels. Intercepting ditch from the minimum grade is 0.3 and a longitude drain ditch from minimum grade is 0.3. So they have an intercepting ditch and dike. Pipe drains because of the pipes and lower resistance of the flow of the water than due to the ditches because of their great capacity of their size. The ideal use of the nearly level wet cut, the installation of the type of side drain shown in Figure 2.9 of the main pipes must be at least 10 inches in diameter and maybe either corrugated steel vertified sewer pipe rated at least rate a little 0.25% to ensure that the water can get into the drain along its length. Corrugated steel must be perforated for the same reason. The joints vertified sewer pipes are open 1.5 inch. The pipes are covered with gravel, cinders, and stones and straw that the dirt cannot get in or clog the pipe. The method of cleaning longitude drains are satisfactory. Longitude drains has been installed. The track supervisor to direct his attention to keeping clean. The pipe drains do not offer serious problems since the storm water washes them clean. B. The method of cleaning longitude drains. Once a satisfactory longitude drain has been installed, the track supervisor has to direct the attention to keeping the plain pipe drains not offer serious problems since the storm water washes them clean. The side ditches requires the deal of attention. Several approved procedures may be followed. The cleaning side ditches that once has been used, of course, it depends on the labor of equability available for the choices as affected by to some extent the density of traffic moving over the rail line. Cleaning the methods can be broken down into two groups: on-track and off-track procedures. On-track procedures involve a work train moving along the track at a slow rate. Speed of the cleaning being done at the rate of the train movements. The work obviously blocks the track of the other train movements and can be used on multiple track lines, whether only on multiple track lines where other tracks are capable of handling the regular traffic. On single train lines where the traffic density is so low that the work train operation does not seriously interfere with the regular train traffic. The vice versa. The chief advantage in the on-track cleaning is that it's economically where large quantities of the refuse must be hauled in the great distance where they must not be necessary, usually most particular to use the off-track procedures. The most common method of cleaning ditches with the work train is simply to employ the force of men and hand tools to clean the ditches, deposit the refuse of the car and work train. It usually requires forces of 18 to 20 men working by hand. Justifying use of the work train on track ditch maintenance may involve using a mechanical ditcher or spreader that uses a steel blade to clean the end, enlarge the side ditch, and since the ditch blocks adjoining tracks onto the mobile track lines, it can be used only when the track is gone to be empty. 2. Off-track procedures must be used, and traffic requirements prohibit the use of work train. Number of track methods available for track supervisor depends largely on the ingenuity training, drainage available resources govern for the method chosen. Only the few methods of mention of the bulldozer, dragline, excavators, crawl cranes, wheelbarrows, if available, and a few implements that they may be used advantage with the contour of the land adjacent for the ditches away from the determining influence of choosing the proper method of high embarks on the fills of the narrow shoulders. Narrow cuts obviously exclude the use of large equipment. Wheelbarrows are often the implements that they can be used in such a location to speed cleaning in wheelbarrows wooden runways after often used. 215. Supplementary drainage. The cross drain is mentioned in the discussion of the classic solution of water pocket problem in the paragraph 2.12. A cross or lateral drain is usually only one type of supplementary drain, and the drainage is needed to dry up the water pockets as diverted in water before it reaches the endangers or the track. The other remedies used to solve the drainage problem are intercepting ditches, cinder trenches, grouting, or French drains. 2. Cross lateral drain. The simplest cross drain and the removal of the valve. Several cribs there if the spaces between the several sometimes pipes driven in the slant roadbed within the side of the chosen. The Figure 2.8, the cross drain types of any water to the form of the water pocket leads into the main side of the ditch to a pipe drain. Lateral pipe drains shown should be at least 4 inches diameter. If the drain problem is severe, it must be necessary to locate cross drains at every one of the half rail length, that is about 20 foot intervals. A procedure often used for the pipe drain is is to have them run on top of the subgrade directly below the ballast and drain the side of the ditch as shown in Figure 2.9. Arrangement aids the flow of the water across for the subgrade, preventing it from seeping into the subsoil. If the soil is spongy and soft rather than solid and impermeable. In addition, these drains lead off the spring water and the springs occur. The roadbed is frequently doing in the water into the wet cuts. Perforated pipes 2 to 3 inches in diameter used in all through vitrified pipe is specified in drainage. Corrugated metal piping and frequently used in short-term military uses. It should be perforated to allow the water to seep through the galvanized asphalt and coated galvanized or asphalt coated to Figure 2.9 cross drain with installation of the pipe drain on the top of the subgrade, prolonging the intervals in which the pipe cross drains are installed depending on the severity of the problem. Intercepting ditches installed with the walls of the wet cut. Intercepting ditches diverting the water before it reaches the track, with a chance of them doing any damage further and preventing the water from running down the face of the cut or causing erosion. The minimum dimension of an intercepting ditch are 3 feet wide by the bottom of the 1 foot deep, and experience shown as these dimensions are not necessarily large, but they must be increased. These ditches must have a minimum grade of 0.3% to move the water away. If the soil is not firm, the water movement in ditches that can cause the scoring that is happening to the ditches must be paved. The asphalt, concrete, stone, bricks in place of the intercepting ditches, dikes, and sometimes constructed at the top of the cut. Cinder trenches. As the system of the trenches is filled with the cinders may be used as cross drains. The location does not require the pipe laterals, but does not need the supplemental drainage of these these drains are formed merely removing the ballast from the cribs and should be in no case be located directly under the rail joint. D. The grouting. One ineffective remedy the water pockets is grouting. Grouting is fluid, a mixture of cement water, cement, sand, water mixture injected under the pressure of the void of the water pocket to force the water seal off the pocket, as illustrated in Figure 210. The commercial grouting equipment is available. French drains. When water pockets are chronic and are located higher than the drainage ditch as fills, and the use of French and rock drains is often justified. Such a drain is constructed of removing filled materials as from the affected area. The replacing it with stones and rock. Water cannot be trapped in the rocks because of many passages between them. The actions curve the water track. The trains are operated over the road while the French drain is being constructed. Some of the temporary support is needed to hold the tracks with the fill. The material removed. The support may be timber shoring, heavy wooden beams, columns that serve as bridges. These members are removed when the stone is in place. 3.5. When the design of a rail section must be determined that the actual measurement of 32nd of an inch of each surface of the section and the cross section of a rail. Note that Figure 3.1, the label applied to the various surfaces of the other section, notable for the topmost part of the wheels known as the head or the ball. The bottom of the section of the rest of the cross tie on the side of the plate is called the base, and the flange, and whether the base and the head is the web. The figure specified in pounds per yard. The rail weighs 100 pounds per yard and is called 100 pound rail is called the 100 pound rail. The per yard being understood similarly. The rail referred to 75 pounds per rails. 75 pounds per rail weighs 75 pounds for every yard of length. The military standard for standard theater issues 85-pound rail and 39-foot lengths. 100 and 115 pounds rail may be found in stateside installations. This is a description of the head base and head web, the depth and head of the fishing height, and the depth of the base, the angle, head of the angle, and then base of the angle 2, and slope head in the center line of the bolts. The first conclusion is that the rails are similar shape, the one more greater than height of the stiffer. The second is that they are made similar to material. Their weight of the proportion is to the cross-sectional area. It is roughly true that the rail varies in stiffness and direction proportion to the square of their weight. Suppose that you compare a 100 to 80-pound rail. Your equation would be therefore a 100-pound rail is 1.6 times stiffer than an 80-pound rail. The first standard railway sections were developed in American Society of Civil Engineering, is known as the ASCE sections, later the American Railway Association, ARA, the American Rail Engineering Association, jointly improved by the design with the two series sections of the RAA and the RAB. The A series was meant The A series was meant for the use of high-speed territory notice of the height and thin head. The B series was designed for the use of heavy curvature of grade and tonnage district noted that its narrow, deep head for the long rail still later, the American Rail Engineering Association, one of the assumed that the task determined for the proper rail section, the heavier the rail, developed but known as the RE sections. 3.9. The length of the T rail sections increased continually since the type of the rail was introduced. For many years, the 33-foot section was standard note. Now, the 39-foot long military standard is most generally used in the United States. The section 39-foot rail easily is under into a standard 40-foot gondola for ease of the transportation. Long rules require fewer track joints per mile, since the joints are a source of continual trouble and expenses of the track maintenance. Any means reducing the nuisance is welcome. Disadvantage continuance of the welding are twofold. First, there is a problem in satisfactory means of welding short rail sections together that make the continuous rail. Second, to the problem expansion of the contracting because of the temperature changes. The solution of the lies in restriction rail movement is by securely fastening the rails to the ties embedded in the ballast. That this action sets up an 3.9. The length of a T-rail section increases continually since the rail was introduced, and for many years the 33-foot section was standard. Now the 39-foot length military standard is usually generated in the United States. The 39-foot railway easily standards and 40-foot gondola aids the longer once again, easy for the transportation, longer rails for fewer track joints per mile. Since the joints are source of continual trouble, expenses of track maintenance, any means of reducing nuisance is welcome. The disadvantage of continuous welding are twofold. First, is that their problem of a satisfactory means of weld short rail sections together to make continuous rail. Second is the problem of expansion to contracting because of the temperature change, solutions to which lies in restricting all rail movement by securing fastening the rails to two ties embedded in the ballast. This action set up and transverse fissure is the most frequent aggravating all of the flaws there is. The transverse fissure is caused by the hydrogen remaining in the rail after the manufacture. The fissure, the crack is the crosswise break straight, starting in the nucleus inside the head of the rail and spreading outward. The failure can be recognized by either the bright or the dark round or oval smooth around in the nucleus, is shown in the example in 3.2a until the rail actually fails in its appearance sounding from the outside. B. Horizontal split head. The horizontal split or horizontal breaks is inside the head of the rail, spreading outward called the horizontal split heads, and are illustrated in the figure 3.2d. They are usually indicated on the side of the head, either the longitude seam of the crack or the flow of the commute metal. See the composed fissure of the horizontal split head, which in the spreading it turns up and down. The head of the rail is caused by a compound fissure. An example is shown in figure 3.2. A vertical split head is for split that may run vertically through the near middle of the head and extend it unto the through, and is shown in figure 3.2e. The such split are called vertical split heads. A crack or the rust streak may be shown under the head close to the web, and a piece may be split off the side of the head. A crushed head. A flattened crushing in the head, as shown in figure 3.2f, is in a crush head. Split web, a crack that runs lengthwise along the side of the web and frequently extended through the web. Such cracks result in what are called split webs. In figure 3.2g, shown as an example. Broken base. Any rail base with a crack or the break in it and can be said to be having a broken base. Not two views is shown in 3.2h is how the pieces are shown in missing square angular breaks or partially complete breaks there is no sign of fissure or any other defects discussed is known as a square angular break deepened in on its shape. Example is shown in 3.21. Pipe rail vertical split usually on the web occurring because of the failure to the shrinkage of the cavity to ignite. The unity is called the piped rail. See that example shown in figure 3.2c. Other failures: fracture of the web at the bolt hole locations of dangerous and arc is discussed in more detail in section 4, which threats joint maintenance. Rail-ended batter is also discussed in section, as well as other failures or specific remedies. A rail section under the United States is generally 39 feet longer section advisable because there may be fewer joints and faulty joints causing most of the work in the track maintenance. The life of ties service depends on the kind of material, amount of the character of traffic, climatic method of preserving treatment of the amount of tie protection devices, tie armor used in constructing the track. The remaining paragraph of this section discussed on the wooden and other kinds of ties and sizing and spacing and wooden tie preservation. Hardwoods, the ash beech. For hardwoods, for ties, there's ash, beech, birch, catalpa, cherry, chestnut, elmet, gum, hickory, locust, black honey, and maple, oak chestnut, red, white, poplar, sycamore, walnut, black. Softwood, cedar, cottonwood, cypress, fir, Douglas, hemlock, larch, tamarack, pine, longleaf, western redwood, and spruce. Top views. A satisfactory dotted line remains on surface. A. Unsatisfactory tie dotted line runs on the surface. Ideal tie. Side views. Unsatisfactory when distance represented by the arrows is less than 2 inches. Satisfactory when nowhere along the center line to the top of the bottom is distance less than 2 inches. A steel tie's advantage of long life, reduced labor and maintenance. The most serious drawback to there is use of that may be twisted and wrecks the tracking destruction, causing removal difficulties. Breakage and the rust necessities and many renewal steel ties causes excessive insulation problems on lines depending on the track circuit signal, and they are noisy and expensive. B. The concrete reinforced concrete ties have the same general advantages as the steel ties. However, they are far too heavy for easing handling, lacking of the resilencing needed to withstand the shocks of railroad traffic, are easily crushed in derailments and cause shorter circuit problems in track circuit territory. For the rails to satisfactorily support a tie should they approach 9 inches of the width. The standard tie length of the United States varies in 8 to 9 feet. The tie thickens through from 6 to 7 inches given in the table 2 are typical tie size recommended for uses. The 9x9 thickness of 8 is a high-speed main line. The 8.5 by 8 by 6 inches acceptable for high-speed services. Military standard. 8 foot by 7 inches by 6 inches permissible but not desirable for mainline. May be used in sidings or yards. The mainline trackage for over 100-pound rail speeds over 50 miles an hour, 50 million in gross tons per mile per year. Number of ties per 30 feet, 20. Number of ties per 39 feet, 24. Mainline trackage over the 100-pound rail, moderate speeds and 7 to 15 million pounds gross tons per year. 18 in between 33 feet and 39 feet, 20. Siding heavily traveled under industrial trail track. 16 for every 33 foot and 18 for every 39 foot. Storage track of the 14 to 16 on 14 to 33 foot rail and 39 foot on the foot ties per foot 39 foot rail. 16. Mainline running track. It's a number of ties per 26 rail. 14 number of per. We got 26 on 14 ties for the mainline running track. It's 30 foot and 60 ties, 33 foot, 18 foot ties, 39 foot rail, 21 foot size. Storage is 26 foot length, 12 per 30 foot, 14 ties, 33 foot, 16 ties, 39 foot, 18 foot. 18 ties. Last 60 feet of the spur track, 10 foot on per 26 ties, 30 foot rail, 12 ties, 33 foot tail, 13 per 39 foot rail, 16. A chemical treatment. Having you ever wondered why wooden ties are so black? Their answer is simply because they were crossitized before being put into the service to prolong the life of preventing the decay of one of the commercial railroad reports. The crossitizing extends the tie life by 10 to 30 years. Care must be taken in handling the crossitized ties, and crossitides burn bare skin and cause them a very similar to poison ivy. When handling them, gloves must be worn outside of the gloves must not be allowed to touch anyone's skin. What you see is a top view over the side views, and you see the anchors of the split curve, and the anchors caught to hold the brakes in the tie. Both hardwoods and softwoods are used, and ideal ties are straight in between the curved and split, slightly straight line drawn, and one end of the does not leave the edge of the tie. The United States standard ties are 8 inches by and placed intended for 8 inches apart for the commercial use of ties. Ties are pressurized, and it looks like they can have the track fastening spikes for rail anchors, braces, gauges, rods may contribute to the efficient track. The other fastening spikes, rail anchors, braces, and rods may contribute to the efficient track. That's where this is down here. Both hardwood and softwoods are used. Ideal ties a straight rate but be curved slightly as long as the straight line drawn in one end to the other does not leave the edge of the tie. The United States standard ties are 8 foot by 9 foot long and placed in 10 in by 18 inches apart. For the commercial use of wooden ties are preserved by the creosote and zinc chloride. Several fixtures are used in fasten part and tracks together. Steel ties plates spread by the train weight over the wide area that does the rail base, keeping the rails and cutting in the tie. The ties are held in the ties head hook. The spikes hold down the pulling of the spikes filled with the soft wood plugs. Screws spikes are used in some European and other countries. Thrust off the rail is resisted in rail anchors, braces, and gauges. Gauge rods are used to hold the track in the proper gauge. The generally used in the curve once is shown in 3.6.17. Only the guided location extent to use the experience. If the track is particularly curved and continual spreading, the gauge rods are justified the track sitting circuit territory. They must be insulated. Several fixtures are used to fasten parts of the track together. The steel tie plates are spread with the train weight over the wide area that does not the rail base and to keep the rails and cutting in the tie. The rails are held and the ties hold. Hook heads are spikes and the holes are left by pulling spikes are filled with the soft wood plugs and screwing spikes are used in some European other countries. Thrust to the other rail resisted to the rail anchors and the braces and gauge rods. The bolts to the lengths of the tightening the bolts securing the bars and the rail contributing greatly to the efficiency of the rail joint. The bolts are used in the splice light rail on either 7/8 or 1 inch in diameter from the heavy rail 1/4 inch. Typical bolts shown in figure 318 and 318B on hexagonal square nuts. The bolt heads are each are either hexagonal square or hexagonal or square shown in one type of the spring. The washer is placed between the nut and the bar, preventing the nut of the working, loosening the section of the bolt directly under the heavy heads as an oval alternative hole to the bar. The oval while the reminder are the oval section of the bolt is filled with the oval bolt hole. The bolt is prevented from the turning of the because of the jarring vibration. The oval holes also serve another purpose. Rails 75 pounds or up are bolted so the nuts are allowing space of the expansion of the rail ends are in the place between the ties. Standard practice of the railroad dictates that how far the ends be. When the joint bars are applied, the railway expensive contracting base of the temperature changes must be provided for the rails laid in hot weather placed together so that when the contracting cold weather that the space rail gap will not be too large. Similarly, the rail laid in cold weather having space between the length and so that the room to the expand joint bars are bolted and made as soon as allowed to the rail to move the small amount within 66. Specially used established placing a wooden shim to the correct dimension between the rail ends. The shim may be left in the space between soon crushed when the rail expands. The metal shim is used to be removed after the rail is fastened because it is interfering with the expansion of the temperatures from 20 to 0. The gap of the 33-foot rail and the gap of 39-foot rail is 5/16 and 3/8 of an inch for negative 20 to 0 temperatures, 0 to 25, 3/16 of a quarter of an inch, 26 to 50 degrees temperature, 1/8 to 3/16 of an inch, 51 to 75 inch, 1/8 of an inch to 1/8 of an inch on a 33-foot rail, on a 39-foot rail, 76 to 100 degrees Fahrenheit, 33-foot is 1/16 of an inch, 39-foot rail is 1/16 of an inch. Over 100, there's no gaps. Degrees in temperature and expansion. Applying the bars paragraph to 325 that describes the track of the bolts and stave and the heavy rail bolted head to alternate outside the inside the rail that the light rail that they do as they direct the crew and applying for the joints parts correcting to make sure that the standard practice in locating the bolts heads are in for the road is being followed by the weight of the rail that you are laying. The bars are in the place and the crew has run in the bolts and the holes in the bolt put on the washers and the nuts. Now comes the critical tightening of the bolts. Either the power of the hand wrench is in inserting the track and the bolts are tightened in with the hand wrench providing the tensions of the track bolts draws and the bars into the place while they are there are first applied in the holes of the bars in place of the two working together in the wrist resist bending. The initial tightening and should be provided enough reserve so that the retightening will not be. C. Spiking. The next step of the spiking the joint, looking again at the sketch of the angle bar near the beginning of the paragraph. Note that the slots of the flange holding the heads of the spikes driven, and that these slots fasten the railway joints of the ties. Sometimes the spikes are drawn against the bar ends. Spiking the joints prevents the railway from creeping out its trains along the rails in those places where the ties are laid directly to strings, such as on bridges, trestles, or with the open floors. The joints are not spiked. The rail must be left free to move on the ties. A. Overall need. The joints are weakest spot in the tracks, depending on the consistent with the attention of the railway maintenance. The crew and loose joints create a bumpy ride as well as noisy. The joints require much expensive work to hold the track surface. Some of the thoughts are brought out of the earlier paragraphs, otherwise mentioned here to the first time, but all in the point of the overall need to the keeping of the rail joints up on the par while maintaining the track requires well-maintained joints. Defects what can go wrong when the rail joint weak cracks, where cracks, breaks, and loose track bolts are some things that can happen. Defects, when can you go wrong with a rail joint? Weak wear, cracks, breaks, loose track bolts, and some of the times things can happen. Where the train wheels pass it over a joint, severe blow is delivered to the end of the next rail, causing the end to be battered. One of the more serious forms of the wear, which rails are subjected, sections on which ends that have been hardened or widened only to decrease the amount of the wear. The ends of the 6-hole joint of the bars are also subject to a great deal of the wind of the wear. Badly battered railway cross, rough riding, damage to the equipment laid, eventually pumping ties below the joints, abrasive action of the wheels grinding on the top of the joint bars will result in wear on sometimes abrasion being found as to be as much as 1/16 of an end in each deep and extended 8 inches into either side of the bar center. From most of the wears, the 4-hole bars occurs in the center. 2. Cracks and fractures. A break joint of the joint bar may start at the top of the continuing downward, often into the bolt hole. Most cracks, however, start either in the spike slot or from the flanging angle. Is often not whether there were bolt holes, cracks, or breaks in the crack bar is not replaced. Loosened bolts, both a rail joint tended to yield to the right, so the under load between the poorly supported rail joint gives under the load lateral thrust that comes from the under the head. The head tends to move the bar away from the rail. The impact of the thrust falls upon the bolt heads of the nuts and loosen themselves, and loss of support results. Renewing a joint bar is one of the more dangerous on-the-track maintenance jobs. Assigning at least 2 men to do the job of the work when one bar is to be renewed, providing a flat protection from when both bars of joint to be renewed. Loose and missing bolts, nuts. Careless maintenance is obvious as when inspection reveals loose or missing bolts. Only new applied bars. The tension of nuts should be checked at least twice within the first 10 days of the after installation. First within the day, sewn again, and with a week and 10 days. I only add when all bolts and nuts are placed in properly tightened can or rail joint. Provide a support that is designed to give. Missing bolt and nuts should be replaced when there is loss is first noticed. Here you see a left-handed and a right-handed stand of a rail and split joint. To insulate a joint, procedures is as follows. The fiber insulator to place between the barrel base and the joint bar base. Insulators bushing are placed around the bolts securing the bar. Fiber bushings are placed under the nuts, and fiber ending post insulators shall be shaped like the rail are placed between the two rail ends with no room for expansion. 3.3. Summary. The railway joints are connected by the straightened by joint bars. Rails are different sizes are joined by the compromised joints and the variation of regular joint made into the fit of the different rail sections unless they were installed in the very hot weather. Spaces for expansion is left between the joints, and standard military practice is for a joint to be located opposite of the center of the other standard military practice is for the joint to be located on the opposite of the other center of the other rail. The track of the railway broken joints in the electrical track circuit territory must be insulated. In some locations they must be bonded. And that is Railway Track 1 Aipd courses. Get Tradoc.